name's Layan, and this summer I worked in Dr. Kogan's lab, and my research focused on investigating stimulation limits for activated iridium oxide film, or AIROF electrodes. The reason we were investigating this is to prepare for upcoming clinical trials of intracortical vision prosthesis. The vision prosthesis is a wireless device consisting of AIROF microelectrodes that are implanted in the visual cortex of the brain. These devices stimulate the neurons to evoke patterns of light in people with complete blindness. There hasn't been much study done on the stability of AIROF with pulsing except for a 2004 study by Dr. Kogan, which showed that AIROF is damaged when polarized to very negative potentials. In our project, we wanted to have a better understanding of the limitations of stimulation with AIROF electrodes intended for clinical use. All the electrodes were tested in phosphate buffered saline with a pH range close to the pH of the body. The electrodes were placed with a reference and counter electrode and were electrochemically cleaned and went through an activation process to grow iridium oxide film on the iridium electrode. After the oxide film was grown, we went through repeated steps of testing with different parameters and using cyclic voltammetry to check for cracking in the film. The main parameters of pulsing that we were changing were the pulse widths, the charge delivered per pulse, and the polarization of the electrode during stimulation. At the bottom of the methods section is a diagram of the measurement we take during the stimulation testing. The main things we look at were the EMC, which is the polarization of the electrode during the pulse, the recovery of the electrode, and the appearance of any inflection points during the pulse. We focused on three main aspects of the stimulation, which were the pulse width, the charge, and the EMC. We looked at the pulse width because changing the pulse width affects the current density. We looked at charge to understand the effect of the charge density and the total charge passed through the film. We looked at EMC because the more negative the EMC is, the more reduced the film is. We tested the electrodes in two different groups, one with only 3 pulse widths at 5 different charge levels, and the second group from 2 milliseconds to 100 microsecond pulse widths with charge values all the way up to 70 nanocoulombs. We checked the electrodes for any sign of failure by looking for an extra peak in the cyclic voltammetry. Overall, we found that we could pulse electrodes to 70 nanocoulombs, which is much higher than the maximum stimulation used in the vision prosthesis, which is 16 nanocoulombs. Although we primarily didn't see failures, in 3 of the 6 electrodes we did see evidence of failure, but unfortunately the conditions of pulsing that caused the failure were different for each one. From this testing, we were not able to pinpoint which parameters were causing the cracking. However, we believe we understand now what conditions are most likely to cause failure with AIROF electrodes. Having a high rate of charge transfer and a very negative EMC value may be leading to cracking. We suggest that to prevent cracking, the electrode should be pulsed at an EMC more positive than negative 500 millivolts, charge less than 60 nanocoulombs per phase, a pulse width greater than 50 microseconds, and an inner pulse delay greater than 100 microseconds. However, we may need to revise these conditions based on the results of our future work. In the future, we plan to investigate how each pulsing parameter contributes to the failure of AIROF. We also plan to conduct some long-term studies of AIROF in vivo versus in saline to better understand the difference between the two. We believe these electrodes can be used for the intended clinical use without any issues, but we'll continue to investigate ways of ensuring stability in AIROF when used for stimulation.